Now, according to the data we took when timing a pendulum, the pendulum frequency versus length appears to be a power function with a y factor between 0.67 and 0.75. This is the result that we got in class today. Of course, this is only our second day of class, and maybe we're a little bit shaky on these constructions, although people seem to be doing quite well. And we only have confirmation of this ratio from one or two students. So we need more confirmation. Is that really the case? And if so, what are the implications of that? So you might consider, and if it's assigned, of course, you need to do it, do this yourself and see if you can confirm this. Okay, now we move on. Down at the bottom here, there's something about constructing a graph with factor 5/2. That means a y factor of 5/2. But that was already specified up here, so we can kind of ignore that. Okay, how do we construct an exponential function? Now, this is my introduction to the construction of an exponential function, and it's very simple, actually, and similar in some ways to the construction of a power function, but different in some important ways. In this case, it's going to turn out it's the y values that are doubling, and also the x values don't double. So the definition that I start with here, every time x changes by a doubling displacement, y doubles. Okay, now doubling displacement is just some constant change in the value of x. And I indicate a doubling displacement by an arrow. So I've got 4 arrows here representing 4 doubling displacements. And there was no y-axis when I constructed this graph. I just threw the y-axis in there. After you construct an exponential graph using this law, you can slap the y-axis down any place you like, and you have a graph that can be used to model any exponential function whatsoever just by labeling the axes appropriately. We'll get to that later. We pick a doubling displacement. We picked that doubling displacement. And of course that's arbitrary too. There's no numbers, there's no scale involved with any of this. And then we marked x values separated by doubling displacement. Okay, each x value is separated from the one before it by a doubling displacement and from the one after it by a doubling displacement. We marked this point on the graph. Okay, now we didn't have a curve at that time, we just marked this point. Then we started doubling our y values. Okay, so this y value is this. Now x changes by the doubling displacement, so x changes from here to here. So the y value has to double. So we come over to here and we double this y value. And then we do the same thing. We have another doubling displacement here. The value of y has to double. The value of y for this x is this. So the value for this x is twice that. It's this. And the curve isn't constructed with complete accuracy, but with construction tools, compass and straight edge, you can construct these graphs with excellent accuracy if you're very careful. And then we got a point here by the simple reasoning that, well, this is a doubling displacement, so whatever the y value is here, it has to double to give us this y value. So the y value here has to be half of this y value. Now, you know, you can take your construction tools and bisect this line segment to find the y value that's half this great, and then you can port that y value over to this point, so we get a point here. So with compass and straight edge, it's extremely easy to construct an exponential graph. And again, then you can slap the y-axis down any place you like. You can use any number you like for the doubling displacement. And there's one little catch, and that is that the basic exponential function is of the form y equals b to the x, or using function notation because we want to get used to that, y equals f of x equals b to the x. Well, if y equals b to the x, then when y equals 0, b to the x is b to the 0. Did I say when y equals 0? Let me say that again. When x equals 0, on the y-axis, x equals 0. So that b to the x is b to the 0. b to the 0 is 1 because any number to the 0 power is 1. There are incidentally reasons for that, which most people don't know. But it's just consistency of the laws of exponents, and we'll talk about that possibly at some point. Now, stop mumbling and go on. So b to the 0 is 1. When x is 0, then y has to be 1. So the coordinates of this point, wherever you decide to slop down the y-axis, have to be 0, 1. So we immediately, when we put a y-axis on here, we have our y scale. Okay, we have no choice about where we put 2, 3, 4, -1, -2, and so forth. We know this much is 1, so to get 2, we do that again. There's 2, there's 3, there's 4. No choice. However, our choice of the x scale is completely arbitrary until we apply whatever the conditions of our situation are. So, if we find out that we have an exponential phenomenon that has a doubling displacement of 7, whatever the units might be, of 7, then we know that this doubling displacement is 7, and now that we know where the y-axis is, we can apply that doubling displacement from the y-axis to get 7 here. Apply it again, we get another 7, that makes it 14, apply it again, there's 21, -7 over here, etc. Okay, so there's a graph of an exponential function, and this graph serves to model any exponential function whatsoever, sort of. I said that. As long as b is greater than 1. Okay, so this is a model for any exponential function as long as b is greater than 1. Now, if b is less than 1, it's equally easy, and we'll see how to construct the exponential graph if b is less than 1. Very easy. So exponential graphs are always very easy to construct.